Okay, now we are going to talk about how to implement graph abstract data type. Actually, we are going to talk about two different implementations. First one is adjacency list. The other one is adjacency matrix. Graph notion is very old. Before graphs are there, before computers even, and when we start to have computers and graph implementations and algorithms, there was no object-oriented programming methodology. So old graph implementations are not object-oriented at all. And through these two implementations, adjacency list and adjacency matrix are coming from that old days, but still we can use these two representations, two methods in our object-oriented methodology. So we are going to use them in adjacency list methodology. For each vertex, we store a list of actually edges that is connected to that vertex. So edges are represented by array of lists. There is a list for each vertex, and each list stores the vertices adjacent to a particular vertex. Okay, and in adjacency matrix, we store edges in a two-dimensional array. This array is n by n two-dimensional vertex array, and each entry in this n by n array represents a vertex between ith vertex and jth vertex, between ith and jth vertex. Okay, so in adjacency matrix representation, we use two-dimensional array to store the edges. As you remember, the vertices are not stored. Actually, they are between 0 to n. Has the IDs from 0 to n-1. Okay, we are going to start with adjacency lists. In adjacency list representation, each vertex has a list, linked list. We are going to use a linked list for each vertex, and we have array of linked lists, and the first element is a linked list for edges adjacent to vertex 0. For example, we can have 5, 1, 2, 3, 4, 5. Means there is an edge from vertex 0 to vertex 5, right? And if we have 2 here, there is an edge between vertex 0 to vertex 2. And this linked list stores the vertices adjacent to vertex 1. For example, 0 means from vertex 1 to vertex 0 we have an edge. Okay, and if that is all, we have vertex 3 here, and vertex 4 here, which are not connected at all. That's possible. So we can represent the graph here with several linked lists. 4 of them are empty, and the first linked list keeps the vertices adjacent to 0, and the second linked list keeps the vertices adjacent to 1. And since this is an empty, there is no vertex adjacent to 3. Vertex 3. Okay. And here we have a little more complicated case. As you see, vertex 0 is adjacent to vertex 3 and 1. So there is a edge from 1 is adjacent to 0 and 3 adjacent to 0. So there are 2 edges. So the vertices adjacent to 0 are stored in this list. So 1 is adjacent to 0 and 3 adjacent to 0, etc. So we have a self edge here, as you see. Vertex 5 is adjacent to 5. 5 is adjacent to 2 as well. Right? So we keep the vertices adjacent to each vertex in separate linked lists. So the structure is array of linked lists. Okay. This is another example. Here we have directed graph. Here we have undirected graph. As you see, this edge means 4 is adjacent to 1. So in this linked list, we should have 4, as you see. And 1 is adjacent to 4. So in this linked list, we should have 1, and it is available, as you see. So we have 1, 2, 3, 4, 5, 6, 7 edges. And for 7 edges, we have 14 nodes in total in all these linked lists. 2, 6, 8, 11, 14, right? There are 14 vertices, 14 nodes in these 5 linked lists in total. Okay, which means each edge here is represented by 2 nodes, this node and this node. Okay, and there is no order between the nodes in a linked list. As you see, 0, 4, 2, 3 represents no order. We shouldn't assume any order between the vertices in a linked list. Vertices or edges. This represents a vertex 0 and an edge from 0 to 1, right? This represents an edge from 4 to 1, etc. So each node in this linked list represents a vertex and actually an edge. Okay. So this is adjacency list. In adjacency matrix, we represent the edges in an n by n array, two-dimensional array. Each value between I and j, the value here represents an edge. We can represent this value to be Boolean value, saying that there is an edge from I to j if it is 1, if it is true, and there is no edge from I to j if it is false. Or we can store an integer value. If this value is 1, there is an edge from I to j, and if this value is 0, there is no edge from I to j. Also, we can store weight value in this place. So the weight of the edge can be stored, weight of the edge from I to j can be stored in this matrix entry. It's also possible. But how are we gonna represent that the edge is not available? If there is no edge from I to j, since 0 may mean an edge of 0 weight, 0 can be considered as a legitimate weight value. So we cannot use 0 as the absence of the edge. We can use maximum integer. We can put max int here to represent that there is no edge from I to j. So we can use positive infinity to represent the absence of an edge. If the graph is unweighted, in that case, we can use 1.0 to signify that we have an edge, and still positive infinity to signify that the edge is not available. If the graph is undirected, the matrix should be symmetric, since if there is an edge from I to j, there should be an edge from j to I as well. These two values should be same for undirected graphs. So the graph should be symmetric. In symmetric graphs, we do not need to represent both upper half and lower half. We can represent only one half of the graph. We usually represent lower triangle. Okay. So the other upper triangle is the same as the lower triangle anyway. Okay. This is a directed graph, and it is represented as in here. And this is undirected graph. As you see, this edge is represented with this value and this value. And here, there are 14 entries which are not infinity. Remember, we have infinity here. Actually, there is nothing. There is no place that's empty. Empty is not possible in memory. So these values are infinity. Actually, they are not shown in the table, but they are infinity. Okay. So this is adjacency matrix representation. How we are going to implement the graph interface? As in other interfaces, we are going to define an abstract graph. We are going to implement some of the features in graph interface in this level so that we do not repeat the same implementation in both list graph and matrix graph. List graph uses adjacency list. Matrix graph uses adjacency matrix representation. For both, remember the graph interface, it requires a edge class. So there is an edge class for both representation. So both can contain an edge. Also, an iterator should be implemented for the matrix graph to iterate through the vertices adjacent to a vertex. We do not need such an iterator in list graph. Why? Because they are already in a linked list. Iterator of this linked list can be used as iterator of, for the adjacent vertices to one. Okay, so no separate implementation for the iterator is required for the list graph. But for matrix graph, we have to iterate through all the vertices adjacent to I.
Hocam sesiniz gitti.
Mikrofonunuz kapalı şu an değil.
Somehow my microphone is turned off. How? I don't know. I don't know, but that's fine. And now you can hear me, right?
Evet hocam.
So where we left, for the matrix graph, we need an iterator to iterate through all the vertices adjacent to vertex I, right? So some of these values are not infinity, means there is an edge between I to J, and these non-infinity values has to be iterated through this iterator. So we need a special iterator to find the vertices adjacent to vertex I. So an iterator is required for the matrix graph. Is it clear? but we do not need a special iterator for the list graph, since linked list has an iterator and we can use that iterator for our purposes. Okay, in abstract class, we are going to implement these methods. So we are going to keep two data fields in the abstract class level, two values. One is the number of vertices, and the other one is whether the graph is directed or not. Of course, we have to have a constructor for the abstract graph. This constructor will just initialize these two values. Of course, it cannot construct the graph, but since it doesn't know what kind of structure is used for the graph, but this constructor can initialize two data fields directed and number of vertices specified as parameters, and we have two getters that is defined in the interface, can be implemented in this level. And it adds two more methods to read the edges, load the edges from a file, scanner, and to construct a graph, to create a graph by using the information in this file. This file will have both number of vertices and the edges in the graph. So by using this file, we can create the graph, and we have to specify whether the graph is directed or not, and we have to specify the type of the class that is going to be used to construct graph. Remember, we cannot construct an instance of the abstract graph, but we have to construct an instance of either matrix graph or list graph, and we have to specify the type here, whether it's going to be a matrix graph or list graph. Okay. So the implementation is simple for abstract graph. It has two data fields. As I said, the constructor will set these two data fields. The getters are simply return the values of these two data fields, right? And this is the last method to create a graph. As you see, it gets the number of vertices from the file, and it constructs either matrix graph or list graph based on the type value here. If type is equal to matrix, then we construct matrix graph. If the type is equal to list, we construct a list graph. And we use number of vertices that we read from the file, and the is directed value, which is passed as a parameter to construct the graph. If the type is not one of these values, then we throw an exception, of course. And after construction, we have to load the edges from the file. Remember this method? This is the method used to load the edges after the construction, to be able to use this method, this not a static method, as you see, this create graph is the static method that can be used by using the class, but this method is not static. We need to have an object to call this method. Actually, the object is already created, so it is assigned to return value. So we can load edges from, we call this method to load edges from the same scanner. And after loading the edges, the whole graph is constructed. So we return the graph that is created. Okay, so this method reads a file and constructs a graph based on that file. Okay. After this abstract graph, now we are going to talk about list graph class. Okay. The list graph, as you remember, requires an array of lists, edge lists. We have an edge class, and we have list of edges, an array of list of edges. We keep an array of list of edges in this list graph, which is called edges, right? As a data field. Of course, it should have a constructor, and it should implement the rest of the methods that is available in the interface, right? So we should have a get edge method that returns an edge, insert method to insert an edge, or check whether there's an edge between source and destination. Also, we have to have an iterator method, edge iterator method that returns an iterator to iterate the vertices adjacent to the source vertex, right? These are 4 methods that needs to be implemented. Rest of the methods are implemented in abstract graph, right? So here it is, the implementation. So list graph is the class that we are implementing, and it extends the abstract graph. Of course, it implements the graph interface. So this is the list of edges, array of list of edges actually. Okay, this is the constructor. In constructor, we call the superclasses constructor first. That has to be done to initialize these 2 data fields in abstract graph. The abstract graph constructor initializes number of vertices and is directed fields. And then we have to construct the array and lists in the array one by one. First, we construct the array. So we have number of vertices, so we construct an array of lists with number of vertices, which has number of vertices elements. So this array is constructed 0, 1, 2, 3, 4, 5, 6 if the number of vertices are 7, but there is no list yet. So we have to construct the lists for all the vertices from 0 to 6. We have to construct a linked list of edges. So, and assign that linked list to, so this will refer a linked list. Linked list will have a head and several nodes actually, right? So we construct this one, but of course it is null. There is no node in that linked list. So we have to construct this linked list for all the entries. Okay. This is the constructor. And to check whether we have an edge from source to destination, we reach the linked list for the source. This linked list contains an edge including this destination, then the edge is available. Otherwise, we don't have an edge, such edge. We should return false. So this is a linked list. We call the contains method of the linked list and check whether this newly constructed edge is available. We give source and destination to construct a temporary edge and check whether such an edge is available in the linked list or not. Actually, we show here that these contains just the value as vertices. Actually, these are edges in this in our case. So it these things are a reference to an edge structure, and in edge we have source, destination, and weight values, right? So we have to create a temporary edge and check whether that temporary edge is available in the corresponding linked list. Remember, the edge class has an equals method, which uses only source and destination. That's why this operation is successful. Otherwise, since we don't know the weight of the edge, we may not be able to use contains method. We have to iterate through all the edges in this linked list and check only source and destination whether they are equal or not. Since equals method of edge checks only source and destination, this contains method works fine for us. Okay. To be able to insert a new edge, this edge has source, destination, and weight values, right? We have to get the source of that edge and access the linked list for that node and add the new edge in that linked list, right? But if the graph is not directed, any edge from A to B is undirected, so it means an edge from B to A as well. So we have to create a new edge from B to A, from destination to source, with the same weight, of course, and add this new edge into list of the destination vertex as well. Okay, so this edge represents two edges from A to B and B to A, so two add methods has to be performed. So to be able to add a edge from 0 to 2, we have to add a new node to here and a new node to here, right? I hope it is clear. Okay, so we have to add two nodes if to perform two add methods to insert an edge if the graph is undirected. If it is directed, of course, one add operation is enough. To be able to get an iterator for the nodes adjacent to the source, actually, this is a linked list of nodes adjacent to source. So iterator of this linked list is what we are looking for. So we can directly return this linked list iterator as the iterator we are looking for. Okay, so we can delegate the edge iterator method to iterator method of the linked list. That's why we do not need to implement a separate iterator for the linked list graph. To get an edge from source to destination, you should return an edge, not only whether edge is available or not, but you should return an edge. So we create an edge. We keep positive infinity as the weight value, showing that the edge is not available right now. And this for loop, we try to locate this target in the edges in the linked list here. Linked list includes several edges adjacent to source. So for all edges adjacent to source, we check whether it equals to target. Remember, the source and destination are used to check the equivalence. If we can find the desired edge, we return that edge with the correct weight value. If we cannot find the edge, we return this target with the positive infinity as a weight, which signifies that the edge is not available, right? If the weight is positive infinity, we can understand that the edge from source to destination is not available. Okay. So this is all for, we have talked about the implementation of all these 4 methods. So this is all for list graph implementation. We can implement the graph interface as matrix graph as well. Again, matrix graph will extend the abstract graph and provide the implementation of these 4 methods that we have implemented in list graph. And it should keep a 2-dimensional array for the edges. So after we created, we can set some of the edges and create the whole graph. It requires its own iterator class, remember, to iterate through the vertices adjacent to a vertex. Okay, and it's not in this book. It's left as programming project to you. So these are 2 implementations. We can implement a graph as matrix graph or list graph. And from now on, there are several ways of comparing these 2 implementations. I'm not going to go into detail of these today, since it will take more than 5 minutes probably. So I'm not going to start talking about them, but I'm going to stop here. Now we know what a graph is, what the graph interface includes, and 2 implementations, matrix graph and list graph implementations of the graph abstract data type of graph interface. So that is it for today. If you have a question, I can try to answer your questions. Otherwise, that's it for today. Do you have any question?